I'm doing this not from a normal location. I'm on campus actually, and I am going through, and I want to do, just as people are working on projects, I want to make sure that I put this out so you kind of get through some of the very basics of pumps, and it's nothing more than wanting to apply this problem. The sense that, in fact, you know that Bernoulli's equation is the elevation energy per pound of material plus the pressure energy per pound of material plus the velocity energy per pound of material, 2G, plus the head of any pump is going to be equal to, along the flow path, the velocity at the second position along the flow path plus the second pressure, the pressure at the second spot, energy per pound of material, plus the velocity at the second spot per pound of material, plus any head loss. And remember that if a system has a constant, and we'll talk about there, a constant area, constant cross-section, the velocity will be constant. So we're going to talk about here no storage. This is Bernoulli's equation. The power equation I want to cover before we go even any farther. And so you can look at the units again. Q, gamma, H. I want you to look at Q and gamma together as cubic feet per second, times pounds per cubic foot. And then what you end up with is the fact that you've got pounds per second, and then multiply it by foot-pounds per pound, and you get foot-pounds per second. So that equation, Q gamma H over 550, starts to make more sense. Equals the horsepower of the pump. All right, so let's take a look at this first, the theory. I'll do it very small down here now, and I'm not going to use a lot more space. But the theory that you have some reservoir down here, right? The reservoir is a free water surface, and then you're taking water out through some sort of pipe, putting it through some pump, and then discharging it someplace here, discharge. And you have to realize that water flows down energy. And so if this discharge has a velocity head here equal to v squared over 2g, this is the energy. It has its elevation energy, no pressure. And if it's flowing down energy, the slope from that has to be positive up this way. This has to be flowing down. However, at the pump, if you now go back to the pump and go back to the water surface, this actually has to be flowing down energy, so it goes something like this. It's down, and you have this concept that the pump is got to kind of suck water and then push water. And I want to then now define two terms. This is the difference between the pump and the free water surface is the net positive suction head. And then we have, in fact, the total head is going to be equal to the head of the pump. It's going to be equal to the static head plus the dynamic head. So total head of the pump is going to be equal to the static head plus the dynamic head. The static head is the head you're pushing against, or the elevation you're pushing against, if in fact there is no flow. But we remember that their head loss is proportional to a velocity head. So as you pump more and more water, you have more and more head loss. Therefore, you get this question of something called efficiency. So you have to realize if you pump way too much water, you're making too much work for yourselves. So the fact is that pumps kind of respond to the conditions, and a fair part of engineering, I'm going to go down to a new sheet, insert, home, new slide, see how that comes in, we'll get rid of that, home, Grab that. Paste. All right, so see how I can do on this. Maybe I can just drag them out of the way here. So it's been a while since I moved around on this one. So I'll move that one out, move that one around. All right, so you have to remember that, in fact, pump curves, as they are known, pump curves, in fact, graph head versus flow rate. And so if there's a given pump, if there is no head against it, they'll push out a certain amount of water. They can only go so fast. And as the more head there is, the farther down you go. So based on the head, they flow, and this is in CFS typically, or more likely, I'm sorry, it's in gallons per minute, is the way these curves work. So depending on how much head they're pushing against, they produce or pump a different amount of water. So if you start with the fact that the head is low, in other words, just the static head, they start pumping a bunch of water, but because they're punching a bunch of water, there's more head loss, therefore they pump less water, and they find this point where they operate at, an operating point. And that's, in fact, a fair bit of engineering goes into the nuance of that. There is one other curve that's actually shown on a pump curve, and that is something called efficiency. And what you'd like to do is you would like to get that pump working at a point where it's most efficient and giving you the water you want. So that's the generals of a pump system, and I'm going to now go back to the more simple system, and mostly this will be then done by sketching. I'm going to go and don't dare do it, but I'm going to try to grab another, dare I do it, a new slide. I'm going to go ahead and grab that and pull it down. That's not so bad. Grab that and pull it down. So pumps are when you're actually putting energy into water. The other thing you want to do is view, review, start inking. You want to think about the most basic system so you can kind of process through what we talked about as velocities generally being in the order of 3 to 10 feet per second, but they can be more. And also, like it or not, the idea of the top end of your velocities is equal to the square root of 2gh. So if you have something falling a distance of 155 feet, it could achieve a velocity of 100 feet per second, or 68 miles an hour. We're usually a lot less than that. There's a lot, smaller flows than this. Water systems often run at about 60 psi. And 60 psi converts 14.7 psi is 33.9 feet of water, and so you can start thinking about water towers 100 feet tall and all that. So that said, how does a reservoir system happen when it's not pumped? Water flows, once again, down pressure. You have a reservoir, you have a pipe, and you have free discharge. So if the pipe is flowing at a free discharge of V, a velocity of V, then it has energy of V squared over 2g, a velocity head. It has its elevation energy, but the pressure is 0, so that would be its energy grade line. And when you are graphing the energy grade line, you are graphing Z plus P over gamma plus V squared over 2g. In other words, the elevation energy per pound of material, the pressure energy per pound of material, or the velocity energy per pound of material, that's what you're graphing. That's called the energy grade line, and that would be the energy grade line here. And the energy grade line here, when you have a free water surface, is actually the free water surface. And so you get, and I'm going to dare try it. I don't do it too often on this machine, but I'm going to go ahead, and that's your energy grade line. It's a straight line between the two. The hydraulic grade line, however, is parallel for the most part through the energy grade line, and it actually goes through the free discharge, and it's separated by the energy grade line by a velocity head. So generally the steps, if you're doing a free water surface or a free flowing problem, and you know the velocity, and usually know the velocity because you know Q, and you know the area of the pipe, that gets you the velocity. Here is the steps. you calculate the velocity head, you draft where that is. You draft this to scale, probably 1 to 41 to 4. You draft up the free water surface here. You draft up the discharge. You lay in one velocity head above it, and you draft a straight line from the free water surface down through that energy grade line of one velocity head over the discharge. You then offset that line all the way through that discharge, and this is what is called a piezometric level. This is the hydraulic grade line. The hydraulic grade line is equal to Z plus P over gamma. It graphs the piezometric level. And then what you'll see is at any one point in the pipe, the difference between the hydraulic grade line and the pipe is actually measuring the pressure. Remember that pressure is energy per volume, and unit weight is weight per volume. Therefore, when you get these, you end up with energy per weight, which in fact is what we know a pressure head is. All right, so that is the basics of pump curve stuff. You realize that a lot of what we'll do in terms of these discussions through your projects has to do with basically this: velocity times area equals Q, and the definition of Q equals volume over time. But we do want you to understand and be aware of Bernoulli's equation being this spot that we set you up with or for because of how it permeates anything having to do with energy. So to finish out these 15 minutes, I'm going to go to one last slide and then talk about what you pay for if you are pumping a project. New slide here. What you pay for is kilowatt hours. And so in fact, if you have the pump and you have, for instance, add-ins review, start inking. If the pressure H in the pump turns out to be something like 50 feet of head, and your Q in cubic feet per second is 3 CFS, and of course you know gamma is equal to 62.4 pounds per cubic foot, or if on the other side, it makes somewhat more sense, if you might have the head of the pump being equal to 15 meters, you might have the Q being equal to maybe 0.3 meters cubed per second, and gamma equaling what? 9,800 newtons per cubic meter. If you take Q gamma H over 550 on this side, you get horsepower, but you really want to then convert that to watts. On this side, it's just perfect. It's Q gamma H. That gets you watts. And if you take watts power times time, you get what you pay for, and that is kilowatt hours. So that's the recurrent cost of pumps. That, in fact, is why you go about figuring out the pump with the most efficiency. All right, so that's a lot. It just is why you kind of, when you go through hydric head, you want to at least have looked at the pumping stuff, and pretty straightforward things that we're looking at here is the velocity head, this trade, which is velocity equals the square root of 2gh, being something you've seen in physics and something that we have to realize is a good part of Bernoulli's equation. You are essentially trading, a lot of Bernoulli's equations is trading the amount of energy you have gets traded between elevation, pressure, and velocity. So if you have a lot of pressure there in a system, you might have less velocity or vice versa. Thanks for listening.